sorry about the mess up, and I will try to save you some time for your coffee and try to finish in time. So today I'll be talking about the fractionalization of single quantum vortices in the multi-component superconductor BKFA.
Okay.
So before I begin, I would like to thank my collaborators.
Recording stopped.
And Julian,
can you say that it's not sharing the screen?
contributed to the theoretical and simulation of this work. And Nico has,
your screen is not shared. They could share the screen.
oh.
Yeah.
Okay. Okay, how about now? Hello?
Yeah.
I'm hearing some echoes. I'm not sure.
Now it should work, yeah.
It's okay? Okay. Alright.
Now it's okay.
It's okay, yeah.
Okay. So the sample is provided by Vadim.
Recording in progress.
So as we know that the fundamental particles in nature are either fermions or bosons, but in condensed matter systems we have the luxury of having particles that are neither bosons or fermions, which are called anions, and they only occur in the two-dimensional systems. And so far we have in gallium arsenide, aluminum gallium arsenide, two-dimensional electron systems that the fractional quantum Hall state that exhibit the fractional statistics, and also in twisted molybdenum ditelluride bilayers. Recently there has also been report of the fractionalization of the charge. And the reason that the fractional charges can exhibit the fractional statistics is has been demonstrated by these pioneering experimental work, which through the interferometric of these fractionalized charges. The first was done in the Memphis group, reporting the interference pattern shifts, which are corresponding to the fractional statistical angles. And very recently, Philip King's group has reported in fractional quantum Hall state of graphene that the telegraph noise has been corresponding to the fractional statistics of the fractional charges. But today I'm going to be talking about the superconductors and the vortices there. And as you know, that the vortex is the dual particle of the electrons in a superconductor. This is can be seen directly from the quantization condition. We know that the electron charges are quantized through this quantization condition of the electronic from the electric field flux. And if we do an integral of an electron over the Gauss surface, and we can get flux, which is E over epsilon naught, where epsilon naught is the vacuum permeability. In a superconductor, we can do a similar thing, but in two dimensions. If we do integral of the vector potential around the vortex core, we can also get a quantity phi naught, which is defined as the Planck constant over charge 2e. If we multiply over the 2e, which is the fundamental charge unit in a superconductor, we obtain phi naught times E star equals the Planck constant, which is the fundamental constant. From this equation, we can see that the charge and the vortices are really playing an equal role as the particles, fundamental particles in a superconductor. As you know, that the electron charges interact with each other by 1 over r squared dependence between their distance. And for the charges with the same sign, they repel each other, and for the opposite sign, they attract each other. For vortices, their interaction is similar in terms of the repulsion and attraction, but their dependence on the distance is 1 over r. And this is a direct consequence of the two-dimensional nature of the electromagnetic force between the vortices. So basically, the vortices, even in a three-dimensional superconductor, provides an ideal platform to realize the two-dimensional electromagnetism, which is requisite for realizing anionic statistics. And back in the 1980s, Wang has already proposed that it's indeed possible, but not in any superconductors you can achieve anionic statistics for the vortices. Besides the conventional Maxwell action for the electromagnetic interaction, we also need a Chern-Simons action, which is written in this form. So as long as this m is non-zero, we'll have this non-zero Chern-Simons term, which will lead to a non-zero phase factor after the vortices circle each other. So from this equation, we can see that when the flux of the vortices are less than flux quantum, the phase factor after the circulation will be neither 0 or pi, which suggests that they will exhibit anionic statistics. And if we plot the waterline of the circulation of these two vortices, we can see that they form two links which are locked to each other. And this is a demonstration of the topological nature of the braiding operations of fractional vortices. So there are different ways to realize fractional vortices in superconductors. One way is by having the so-called charge 4e or even 6e pairing, because once we have the 4e or 6e in the denominator here, we immediately get a fractional flux vortices in the flux. So this is actually proposed by Berg, Fracking, and Kivelson in the 2009 in this paper on the Cooper superconductor. If you have a PDW state stacked on top of each other, you can realize this so-called charge 4e superconductivity. And also recently in the Kagome superconductor, there has been some demonstration of charge 4e or 6e interference effect. However, this is not an observation of the fractional vortices. So there's actually a different route to achieve fractional vortices in superconductors, which is through the multicomponent order parameter. So we know that in Landau's paradigm of symmetry breaking for describing a superconducting phase, we have a complex field to describe the superconducting order parameter. And this complex field have both an amplitude and a phase. And what vortices are basically phase singularities in this complex field. And if you circulate around this phase singularity, as I mentioned, you will get a flux quantum. And Igor has proposed that in a multi-component order parameter, you have more than one complex field, which forms this kind of a vector form. And each of them is a complex field that describes the order parameter in the ice electronic band. And the vortices are basically the phase singularities in any of these complex fields. And they are defined as the phase winding on the ice electronic band. So that the total flux of all the fractional vortices are still quantized to phi naught, but the vortices on any of these components are no longer quantized, and they can be a fractional of this phi naught. There are many other consequences of having a multi-component order parameter, such as having domain walls in the order parameter or forming a more exotic topological excitations, which are called skirmions in a superconductor. And recently there are STM work, which you might hear soon, about the fractionalization of forming domain walls in these multi-component superconductors. So the material platform to realize a multi-component superconductor needs to have multi-bands crossing the Fermi level. And the iron-based superconductor, barium, potassium, iron arsenide, is such an ideal material platform. Professor Hong Ding's group has showed very, very early on through the RPAS measurement that this material has more than one bands crossing the Fermi level, and the superconducting gap are quite different for at least two of them. Vading has shown in this very nice work that this material has it breaks time reversal symmetry when the doping of the potassium is around 0.7 and between 0.7 and 0.85. He showed further that if the doping level is at 0.77, the so-called magic doping, the phase factors between these different components are locked from each other, and the phase angles are neither 0 or pi, so that it breaks time reversal symmetry this way. Through this S plus IS order parameter, breaking time reversal symmetry, we can realize possibly fractional vortices there. And indeed, as you may have heard from Yusuke, Ken Moller's group from Stanford in 2023 have observed fractional vortices in this BKFA system when the doping is 0.77. And the key things they have found is that besides the conventional vortices, they find vortices which has a much smaller contrast, and the integral of the flux around the vortex core are much less than a conventional vortex. And the total flux increases with temperature and until the temperature reaches Tc. However, there are also some mysteries, even though it has stirred a lot of interest within the community, including us, which is that they have only observed one component of the fractional vortices. As I mentioned earlier, the total fractional vortices should sum up to phi naught, but it's still missing from their measurements. And also because this fractional vortex is decreasing in amplitude with decreasing temperature, it is very difficult to observe fractional vortices in the temperatures away from Tc. So these are sort of the motivations for us to study this material further. So we used a similar technique, which is the scanning screw technique, which you may have heard already. But just to briefly recap, a squid is a flux to voltage transducer that converts the flux through its superconducting loop to a voltage across this loop. And since the voltage is modulating with the total flux through it in a period of phi naught, and we can measure the voltage very precisely so that we can know the change of the flux very precisely. A direct way of measuring vortices or other magnetic samples is by directly putting a squid very close to a sample. And because of the sensitivity, you can measure very small magnetic field or magnetic moments that way. For example, if you have a magnetic dipole, its magnetic field is decreasing with 1 over r cubed. If you put the squid away for, say, around a millimeter scale away, the magnetization sensitivity is on the order of 10 to the minus 6 EMU per hertz, which has been very powerful actually, and has been widely used for material characterization in the bulk systems. But however, if you can move your squared probe to be very close to a sample, say around 1 microns, then the sensitivity of magnetization increases to 10 to the minus 17 EMU per hertz. So this really demonstrates that if you want to achieve very high flux or magnetization sensitivity, and also performing some microscopy, you need to be very close to what you are detecting. And this is the method that has been engineered by Professor Zeldorf group, and they basically make a squid on a fiber tip, and they can bring this tip very close to the sample, so that they can achieve very high flux sensitivity as well as performing a very high spatial resolution magnetic imaging. And we are adopting another route, which is making the squid on a silicon chip. This is called the on-chip scanning squid. And we follow the technique developed by Mark Ketching and John Cutley, also in the 1980s. So basically, they fabricate all the superconducting loops and the Josephson junctions on a silicon chip, and they incorporate a radiometric design so that the background magnetic field can be cancelled. And they also have superconducting coils inductively coupled to the squid so that they can perform flux feedback. And also there are so-called field coils, which is circulating around the pickup loop so that we can perform susceptometry. And I have been developing this technique in the last 10 years, and it has been working well for us. And so the benefit of having this kind of design is, besides the high flux sensitivity, we can perform feedback operations so that we can obtain the absolute value of the flux, which is super important for determining the exact value of the flux. We also have field coils for measuring susceptometry so that we can determine the superfluid density through diamagnetic measurements. And there's also a downside with this kind of a technique, which is that the pickup loop is very far away typically from the sample, and so that the spatial resolution is not optimal. So we have came up with a technique to print a superconducting tip, superconducting needle on top of the pickup loops to enhance the spatial resolution without sacrificing the capability to perform flux feedback and the susceptometry. And we have demonstrated that in principle it works, but we have also enhanced the spatial resolution, but we have yet to achieve the optimal spatial resolution, but we are working on this. And we have also developed some scanning squid, ultra-high vacuum scanning squid, in connection with other kinds of characterization as well as sample growth capability, so that we can study superconductors as well as other quantum materials in the two-dimensional limit. So our scanning squid microscopes have three major modes of operation. One is called magnetometry, which can be used to image vortices or magnetic domains directly. You can also apply a current to some device and measure the flux generated by those currents, which we call the current imaging. And we have used it to image topological insulators or quantum loss Hall insulators, and saw the chiral edge currents in these devices. And the third is called susceptometry, and we can use it to determine the superfluid density of superconductors, and it's also very sensitive. As you can see that we have successfully measured the diamagnetic susceptibility of a monolayer of bismuth 2212. And but we still face one challenge in measuring the fractional vortices, which is that the flux of fractional vortices are very weak when the temperature is very low, meaning it's far away from TC. And we have used this technique, which seems to work quite well, which is that we put our scanning squid chip on top of a tuning fork. And since the tuning fork has a resonant frequency on the order of 10 kilohertz, we can lock into this frequency to demodulate the flux at this frequency so that it acts as a vibrational oscillator, so that we can get even higher flux sensitivity. So to test that it indeed works, so we measure a integer conventional vortex in BKFA. The top rows are the so-called DC flux, which is the straight flux signal from the squid, and they look circular and nice. And the second rows are from this so-called demodulated AC flux signals. As you can see, they are slightly distorted from the circular shape of a conventional vortex because the demodulation is, in principle, measuring the gradient of the magnetic field rather than the direct magnetic field. But you can also see that the contrast has enhanced in these AC flux images, so that we can make sure that we are indeed measuring the vortices. And after doing the integration over the DC flux, we can see that indeed these conventional vortices does not change with temperature until TC. Now, if we look at the fractional vortices at a conventional vortex and a fractional vortex at low temperature, so we can immediately see that the AC flux signal can indeed detect a fractional vortex. However, its shape is quite different from a conventional vortex. Basically, it has a very elongated shape that's longer in this vertical direction. And as we increase the temperature, you can see that the fractional vortex has a stronger contrast, and it's even increasing up to 10.57 Kelvin. And this is consistent with the three-component GL modeling done by Igor. And then we measured other vortices, which seems to have a flux value integrated to Phi naught. However, as we increase the temperature, we can see that the fractional vortices are sort of deforming, as you can see from this rows in the AC flux images. And to around 10.52 Kelvin, you can see that it splits apart into two fractions, the upper and the lower part. And the upper part becomes stronger and stronger as the temperature increases further. And at around 10.93 Kelvin, the two parts have almost equal intensity. And as you go further higher, the top part becomes stronger, while the lower part is weaker. And around 11.11, the lower part diminishes. So this is very interesting because it suggests that this seemingly conventional vortex actually splits into two fractions. And it's also very clear from the change of the intensity that the flux are transferring from the lower fractions into the top fraction, which suggests that there kind of entanglement between these two fractions even after they split. And there are also more finer features which seems to have opposite sign from the two fractions, which we tend to call it anti-fractional vortices, but we didn't have enough scanning area to really tell. And if we do an integral of the flux of these two fractions, we can see which are displayed here. The lower fraction are these blue circles, and you can see its flux is decreasing as we increase the temperature. And the upper fraction, these red points are increasing. But if you sum up the two, which are shown as these black dots, the total flux is always by naught within the arrow. So this seems to suggest that these are the two main components of fractional vortices. Although there could be other fractions in this lower fraction, because when we measure the isolated fractional vortex, the total flux are about 2 times of this lower fraction or upper fraction here. And Julian has done some modeling for us using a 3-component autoparameter with broken time reversal symmetry. And the qualitative behavior is consistent with our measurements. However, there's a caveat, which is that their modeling actually only works around TC. And as you can see, our measurement actually goes down to very low temperatures. So there are also some other features from the splitting motion. One is that the distance between the upper and the lower fractions, they actually do not change monotonically. So it tends to increase as the temperature increases, but then it comes back again at this temperature. So this is kind of consistent with the fluctuation very close to TC, which has been reported earlier in these material systems. Also, we observed N-type vortices, and its splitting can also be seen, which is shown here. So the qualitative features and are very similar to the positive vortex, and the total flux are also add up to 0. And recently we have also seen some merging of fractional vortices. These are 2 fractional vortices, as you can see, and as the temperature increases, they become a single one, sort of, and until it diminishes around TC. So this really suggests that the splitting of the fractional vortices are a metastable process. As an outlook, we can apply a current through the field coil to manipulate these fractional vortices, and we have done this in another iron-based superconductor, iron selenium tellurium, where we have been able to flip the polarity of vortex and anti-vortex pair. So this could be potentially used to manipulate fractional vortices around each other to do the braiding operations, but we still need some readout schemes to demonstrate its fractional statistics. I think my time is almost up. So let me just summarize. We have developed scanning squid microscopies, which has a good spatial resolution and different modes of functionalities, which are suitable for the study of unconventional superconductors. And using this technique, we are able to observe the splitting of a single flux quantum into fractions in a multi-component superconductor BKFA. And this material can potentially serve as a new material platform to explore the anionic statistics of fractional vortices. And at last, I would like to thank my hard-working students, past members and current members, Bin Kexiang, Pan Yingping, Lin Yishi, Wang Shiyuan, and Qi Zhizhou has done the major measurements for this work. And with that, I would like to thank you for your attention.
So any questions for the speaker? Yes, please.
Okay. Yeah. Thank you for this very nice one. So I was wondering, so you showed that the fraction vortex fraction is a different location. The fraction vortex has a different temperature dependence. But the sample, our result is a very ubiquitous, same temperature dependence over the 100 micron scale region of the sample. So did you